I suggest we get cracking today. We get cracking because I want to make sure we get on with the maths. So again, I'm Bobby Seagull. I'm here with Explore Learning, Explore at Home, and we're about keeping the education going. So normally I'd have a board here, but I've moved that out of the way. So go to explorelearning.co.uk to book a free trial, and Explore Learning _official on Instagram, and Explore Tutors on Twitter, and I'm at Bobby _Seagull on all social media. So let's get started. Okay, let's do our positive maths wrap at the start because we've just made it. Somehow we made it. We're gonna power through today's lesson. So it's gonna be like this. Remember the cross? Remember the cross? So 1, 2, 3, go. Yes, I can do maths. Yes, I can do maths. Yes, I can do maths. I need a new one for the computer. Okay, so let's go. So today we're going to be covering time. Let's look at some of the basics here. Let me move my camera slightly down so you can see a bit more on the board. So here are the basics. So we know in 1 minute, how many seconds are there? 1 minute, 1 minute has 60 seconds. Always just checking these things. They seem really basic, but it's good to check. 1 minute, 60 seconds. Then we have in 1 hour, we have 60 minutes. Yeah. And then in a day, 1 day, so for 1 day, there's 24 hours. These are the basic units of time that we all need to be confident of. 60 seconds in a minute, 60 minutes in an hour, and 24 hours in 1 day. And in the last session, we actually looked at why this was. Why is it 60? And some of you told me the Babylonians. So these are the ancient culture in Egypt that actually counted in 60s. And I had some wonderful homework. Athena Watson's son submitted something saying that the Babylonians counted in 60s because 60 has lots of factors. Factors are numbers that go into it. So 1 goes into 60, 2 goes into 60 exactly, 3 goes in, 4, 5, 10, 15, 20 has lots of factors. Okay, so what happens when we're trying to count in more than 60? So imagine I say to you, it takes you 70 minutes. 70 minutes, yeah? 70 minutes to go for a walk. How do you work out how long is in hours? I think we can do this. Draw a line there. That's 60 minutes. That's 1 hour. What's left? I'll write that a bit bigger for you. What's left? 70 less the 60 is the same as Beatrice, 10. 10 left. That's 1 hour and 10 minutes. 1 hour and 10 minutes. So these are the basics. We're going to build up. A bit. Secondly, what about if we change the time to, let's say, 145 minutes? 145 minutes. How long is that in hours? How long is that in hours? And what I do again, boys and girls, is I'll set a timeline. The timeline there, we count in 60 minutes. We count again, another 60 minutes. That takes us to 120 and 25 left over. That is 2 hours and 25 minutes. 2 hours and 25 minutes. And you know what, boys and girls? We can do this for anything. The same concept of building the time up. Well done, Jaylan. We can build this concept up anywhere. So, does anyone remember the London 2012 Olympics? Do people remember that? Maybe some of you might have been small, but your parents have said they were amazing. So in London 2012, there's an amazing stadium called the Olympics. Great name. It took 34 months to build the stadium. 34 months. The question you could have is, how long is 34 months in years? How long is it in years? So what you should think is, last time when we were counting in, minutes, we divided by 60 essentially. Here we think, what's the base unit? In 1 year, there are how many months? 12 months. So, again, we do a timeline. 12 months. Count again. Count for me. 24 months. count again. Oh, too much, too much. So it's 1 year, 2 year, and to go from 24 to 24, we add 10. So it's 2 years and 10 months. 2 years and 10 months. So it's all about the base. And I'm going to type a question for you that I want you to answer. I'll read it for you. You got it at the same time. Well done, Cluin and Sean, for getting the answer correct. So here, if I can type it, if my typing still works. So here's the question for you. Let's say if I can get it up, question. So imagine the Apollo spaceship. The Apollo spaceship. It took the Apollo spaceship. I'll type it here for you. It took 52 hours. It took 52 hours to get to the moon. Yeah, get to the moon. So I'll write this down and I'll put it up for you. Get to the moon. And 52 hours back. And 52 hours back. If I can move the mouse here. And 52 hours back. It took 52 hours to get to the moon and 52 hours to get back. How many days did it take altogether? How many days? I'm going to publish this for you. How many days altogether? 52 hours to get there and 52 hours to get back. How many days altogether? And I'll publish this for you now. Have a look. So the Apollo spaceship, the question's up there for you. So I'm going to put my brain, give you a minute to think about this. It took 52 hours to get to the moon and 52 hours to get back. And that's quite quick. And this is in 1969, Apollo 11. How many days were there altogether? I'll give you a bit of time to think about this. I can see Cledwin's got the right answer. Well done. It took 52 hours to get there, 52 hours to get back. And give me a minute to think about this before I go to the answer. It's quite impressive to get to the moon. It's very impressive. Let's have a look. Let's see what answers we've got here coming up. How many days? 52 hours to get there and 52 to get back. Hopefully you can see the question being published there. I hope. Let's see. Lena, well done. Let's see, Sathina, Cheryl. Lots of great answers. Greg, Michelle. But let's go through the answer. Let's go through the answer now. I'm going to close the card now. I'm going to leave it up there for a second if you want to type answer. So, 52 hours to get there and 52 to get back. So don't forget, you add the two and we get 104 hours. Seems quite quick. And then we work out, let's have a look. And then we work out how many hours in each day. It's 24 hours. So we count up in 24. So we've got our timeline. So we've got 24, takes us to 48. That's 48 there. Then we add another 24, 72. Another 24, 96. And what's left over? As you said, 8 hours. So it's 4 days, 1, 2, 3, 4, 4 days and 8 hours. I saw a few of you getting it correct. So well done, well done, Bo. Well done, Irene. You got the correct answer. It's 4 days, 8 hours. And that's amazing how maths can help you look at things like, oh, the spaceship traveling. And it's all about time conversion. Time and conversion. Okay, so I'm going to have a quick look at bus timetables. Bus timetables. This one here, you're going to have to look at my my board here. So this is an old school bus timetable. So we're going to do a bit of role playing here. Imagine, come on, Mr. Seagull, board the Seagull Train Express. The Seagull Train Express. We're taking a journey back into American 1860s in America. 1860s in America, where the trains are first being set up. So we're going to do a little train timetable for you. And if you can copy this up, that would be great. Imagine we've got a town, yeah? A town called Alda. A town called Alda. Then we've got another town called Bill. A town called Bill. And then a town called Cody. So these are towns in America from an original bus timetable. And now, it will tell you when the buses move. So copy this for me, yeah? Copy. Can you see that for me? Can you see that? So I've written the times really big. So there's Alda, Bill, and Cody. 3 different time zones or bus stops. So the first one is 7:53. It leaves there. Then the next one is, let's say, 8:22. And the last one is 9:12. So there are 3 different times there. I'll pick another one here for you. Let's say it's 8:53, 8:53, then 9:22, and the last one is 10:12. Let's just look at the basics. Let's look at the basics of this. I covered this last time as well in Key Stage 2, but how can it get more complex? So firstly, this bus here at 7:53 starts at Alda and it moves to Bill. Here's a good question. The question is, how long does it take to get from Alda to Bill? How long? So you leave Alda at 7:53 and you're trying to get to Bill at 8:22. How long does it take? How long does it take? Okay, let's do this. We're going to count up. 7:53 to 8 is 7 minutes. Yeah, so we've got 7 minutes there. Then 8:22 is another 22 minutes. So it's altogether 29-minute journey. 29-minute journey. 29-minute journey. Okay, let me remove the question from the section. There we go. Okay, the question should be gone now. Thank you, Cledwin, for letting me know. Now another one could be is, imagine you're having a long journey from Alda to Cody. And let's say you're getting, I'm going to change this one, it's a bit more delayed. This one here is going to be 10:22. It's a slower bus, 10:22. You're going from Alda to Cody, and it leaves Alda at 8:53 and gets to Cody at 10:22. How long does that take? So can you all work out for me, from Alda to Cody, it leaves at 8:53 and gets into Cody at 10:22. How long does that take? So some great answers coming in for the first one. Dean, Bo, Noreen, Irene. You got the first one correct. Well done. So now the new question is, Alda leaves at 8:53 and it gets to Cody at 10:22. How long is that? Okay, I'm going to go through this with you. So we go from 8:53, like chunking. You know chunking in maths? Chunking in maths. So you come 8:53 to 9, that's 7 minutes. Then we've got an hour. I'll put that as 1 hour, or 60 minutes, 1 hour. Then we've got, that takes us to 10. Then we've got 22 minutes left. So it's 1 hour plus 22 plus 29. So well done, Meter and Cledwin, you got that correct. So it's 1 hour and 29. And that is a bus timetable in old America in the 1860s. And the way they can make bus timetable complicated is they might miss out certain bits. They could say, there's no bus here. There's no bus particular slot. Or you could have buses being delayed. Imagine I said to you, you get the bus from Alda to Cody, but your bus is delayed by half an hour. What time do you get to Cody? And that would be 7:53 to 9:12. And then we add half an hour. So 9:42. The timetables can get complicated, but the key thing is they're really practical. They're really good bits of maths in everyday life. So next time you go outside and you go to a bus stop, or even on the internet, have a look at bus timetables. See if you can make yourself a question or work out, how do things work there? So that's bus timetable. So now we're going to move on to the next part. Well done to Lena. Someone's asking me, Ronak, was my dad angry about the broken clock? Can I tell you what? The gods looked on me favorably because the clock actually was fixable. My dad himself, so Mr. Seagull is saved. He was saved from the anger of his father. So thank you for asking. Okay. So we're into the next section. And then the last and main section, this is something that Key Stage 3 would cover specifically. And I don't think you do too much in Key Stage 2. So if you're a Key Stage 2 student, really get your brains on. Really get your brain in gear. Okay. So imagine this story here. You know, in isolation, you decide, I'm going to go for a walk. You go for a walk for 1 hour. You go for a walk, yeah? About 6 kilometers. Then you take a 30-minute rest because you're a bit tired there. And then you walk back again for 1 hour. Sounds like a simple story, but actually we can represent this as a graph. And this, boys and girls, and carers, adults, parents, I love about maths. Mathematics and graphs can tell stories. It's not just books. I've got books in my shelves here. Words can tell stories, but so can graphs. Let's have a look. Remember that journey. So, can you get your pen and paper? If you've got your pen and paper handy, get it out. And I want you to draw 2 things for me initially. And these are called axes. Axes, yeah? They're called axes. And this is along the corridor, the x-axis, and that's the y-axis. You've got the x-axis and y-axis. X-axis and y-axis. So, in my story, I said at 9 o'clock, so this bit here, this x-axis, is our time. Is our time. Okay, put that down. And then our y-axis is distance. I'm going to write that there, distance. And distance in, and you always put, boys and girls, always put your unit. So time in, I'll put hours. And then distance in, we'll put in kilometers. So distance in kilometers. Distance in kilometers. So our time, we start walking at 9 a.m. And do people remember how long I said I'm going to walk for? I said I'm going to walk for an hour. 1 hour. And it's going to take me, how long? 1 hour, and I'll walk 6 kilometers, yeah? 6 kilometers. So here, we've got 6 kilometers there, and we walk for 1 hour. So what you do is you find 1 hour, you found 10 o'clock there on your graph, and you put a little dot there, and you join it all the way up. So all it tells you is you've walked at a constant speed, the same speed, you're not running and sprinting and slowing down. You walk for 1 hour, and you get 6 kilometers far. That's 1 hour. And do what I said after that, you're a bit tired, you're like, I've had a long walk. And you have a 15-minute rest. And a great bit of maths by Cledwin. Cledwin says 6 kilometers an hour. That's actually the speed. The speed is the distance over the time. So you walk 6 kilometers in the hour. 6 kilometers per hour. Then you have, how long should we have a rest for? Half an hour? Half an hour rest. So you go to 10:30 there, you draw a little dot line, and you stay there. You're not moving, are you? You're staying in the same position. Bo is correct. You stay there for 1 hour. You travel for an hour. You stay in the same position for 30 minutes. And now we return back. And how long is it going to take us? Actually, let's say, I actually said an hour, but we're going to walk back really slowly, yeah? Really slowly. So the time is now 10:30, and we take an hour and a half. I'm going to be slow. I'm going to be a bit slow and ambly because I'm getting on. If it's 10:30 and it takes us an hour and a half to walk back, it means we'll return at 12 o'clock. You've got your piece of paper and your pen. Draw that for me. And this, boys and girls, is a mathematical story. It's a mathematical story. And we can do another one in a second. But this is wonderful because it shows you someone left their house or left their point of origin at 9 o'clock. They left and they moved at the same speed, same line. The gradient is the same. Have you heard of the word gradient before, people? Oh, I'm going to do a shout out to someone else later for their birthday. I'll do it at the end of the lesson. So, this gradient is how steep something is. Have you ever been cycling or walking where really flat? Okay, it's a flat road. There's no gradient there. When it's slightly inclined, you're like, oh, it's a bit slow for me. And when it's really steep, it's like, whoa, I'm really tired. Well, this bit tells you how fast they're going. The steeper it is, the faster the gradient. The steeper it is, the faster the gradient. Or the higher the gradient, the faster it is. The other way around. So here, let's recap it. 9 to 10, this person walked at a constant speed for 6 kilometers. Then we know because it's 10:30 here, they stopped. Then they returned back, and it took them an hour and a half. And that's a simple journey represented mathematically. So we're going to do one question. question here together, and I'm going to get you to think about what this means. I'm going to get you to think about what this means. We'll do one example, and I want to come to. We're going to get a famous man appearing in our lesson today. So here's a more complicated journey. Can you get your piece of paper? It looked like a trapezium. Amisha said, yes, trapezium had a two parallel sides, but they were parallel, meaning they're the same distance apart. But the bottom part was longer than the top part, and then we had the side. So that was a trapezium, Amisha. Well done. So get your piece of paper. We'll do one more example of this before I set your question. So can you draw for me your x-axis and your y-axis? Yeah, x-axis and y-axis. And the gradient is not a good question by Cledwin. The gradient tells you how steep the line is, how steep. So if it's really flat, if it's like that, that's a shallow gradient. If it's like that, that's a really steep gradient. And on these graphs, the steeper it is, the faster they are. So it's the steepness. That's the key word. The gradient is all about how steep that line is. And for a distance time graph, it tells you about the speed. We're going to come to Mr. Seagull loves doing little mouse raps. We're going to do one right now, but we need to set it up. So again, the x-axis is the time. We're going to put hours again. So right again, please copy up the second one, time and hours, and the y-axis is the distance again. So put down the distance for me on your paper, and I'll do kilometers again. So kilometers. So in maths, I was talking to a maths teacher, one of my friends called Susan Okereke, and she said to me, we've got the x-axis and the y-axis. Why can't we switch them around? And here's a bit of maths. The x-axis is the independent variable. And what it means independent is the time will keep going. It doesn't matter if I'm having a lie down or I'm playing football or I'm running. Time will keep ticking along as usual. But what is the dependent one is the y-axis, because that changes. If you're going really quickly, that moves. If you're slowing down or you're stopping, it doesn't change. So the y-axis is called the dependent. The independent, and this is the dependent. So the little way of I've got for this is, so time is independent, time is on the x-axis, distance is dependent, distance on the y-axis. We'll do that again a couple of times, all right? Time is independent, time on the x-axis, distance is dependent, distance on the y-axis. We'll try that. So time is independent, time is on the x-axis, distance is dependent, distance on the y-axis. Okay? We'll try again. Remember? Time is independent, time is on the x-axis, distance is dependent, distance on the y-axis. That's we'll refresh ourselves with that at the end. Yeah? This is called, remember? Time is independent, time is on the x-axis, and this one is dependent, distance on the y-axis. There we go. Independent, dependent. You've learned something which again is used in science as well. When you progress 7, 8, 9, 10, don't tell me this is very cheesy. I like cheese. I like gorgonzola, parmesan, cheddar. Cheese is good. Not too much cheese, but a little bit of cheese. So, if you look at this journey here, we'll do a quick journey. So, someone, let's put an axis. This is a cycling race. Let's put 60 up there. Put 60 for me at the top. Can you put 60 there? And we'll split it up. So we've got 30 over here. So 60 at the top and 30. 60 and 30. Okay. And this particular journey, let's draw. So we're going to start at 9. I like starting at 9. So we've got 10. Draw. For me, remember one really key thing, boys and girls. They should be equally spaced out. So 9, 10, 11, 12, and 1, and 2. So you've got your piece of paper. It says 9, 10, 11, 12, 1, 2. For a few minutes more before we start moving to the conclusion. So I'm making sure you still get your half an hour of learning. Mr. Seagull, 30 minutes, what we all need. So Let's have a look at this. This particular journey, someone's cycling. They're cycling quite fast. Or let's just say cycling. Let's say they're running. They're a runner. They're a runner. You can be anything you want. So they run. They're a professional runner. They run for 2 hours. They run for 2 hours and they reach 30 kilometers. Remember, 2 hours is 11 o'clock and it goes to 30 kilometers at the same speed. Yeah. And now they run for 2 hours. 2 hours, 30 kilometers. You're going to be tired, aren't you? You're going to be tired after that. So they decide, let's have a hour rest. So 1 hour, 1 hour rest. Yeah? 1 hour rest. And now they say, actually, what we're going to do is, we're going to sprint. Now we're going to do some sprinting now. We're going to do sprinting for 15 minutes. 15 minutes. So 15 minutes is a quarter. What's a quarter of an hour? 15. So they sprint, and I don't know how they do this. I think they probably get on a bicycle now. They get on a bicycle and they carry on their journey. 15 minutes takes us to 60 kilometers. They're definitely on a bicycle now, yeah? They're definitely on a bicycle. 30 kilometers in 15 minutes. And now they cycle all the way back home. Back home. You can see this is a journey. This is a journey. They start at 9, go for 2 hours, 30 kilometers. And can you tell the gradient? I want you to use a mathematical word. This is a gradient. This gradient is steeper, and that means they were quicker. You can make statements about this just by looking at the diagram. And here's the cool thing. I don't know anything about, imagine I just came into this lesson like, whoa, what's going on in this lesson? This is where they started returning home. And that is what? 12:15. Without knowing the story, I can tell at 12:15 this person returned home. There you go. So here's a cool, it looks like a mountain, someone says. Sort of, it does. Here's the thing, before we wrap up. So, who is the fastest runner in the world? Who's the fastest runner in the world? I want to show you how speed, distance, time is in real life as well. Who's the fastest runner in the world? Give you a clue here. It's Usain Bolt. Usain Bolt, the fastest man in the world. And I'm going to show you a speed, distance, time graph, him and mathematics. So let's have a look. Remember, we draw the x-axis and the y-axis. Remember, the x-axis is always going to be what? The time. And that's going to be in seconds. And then the x-axis is the distance. And this time it's going to be in meters. Remember our little rap? Remember? Time is independent. Time on the x-axis. Distance is dependent. Distance on the y-axis. So we do it again. Time is independent. Time on the x-axis. Distance is dependent. Distance on the y-axis. So we got this. We got a few answers. Satina Bo says it's Usain Bolt. Yes, we know it's Usain Bolt. So, you know, Usain Bolt, people often think he gets quicker towards the end of the race. But actually, the maths proves he doesn't. So, he's ready. I'm ready and willing to go. Waiting for the gun, yeah? He's nervous. The gun goes. And he takes a bit of time to get out of the blocks. So initially, so call that about under 10 seconds, initially he's quite slow. He's quite slow. So the first 10 meters he's quite slow. But then he starts picking up pace. He starts picking up pace. And I'll tell you what, boys and girls, by the time he gets to about 35 meters, that's when he starts reaching his top speed. And you can tell in the graph, can you see it's getting steeper and steeper, the curve? It's getting steeper and steeper. It's getting quicker. And when runners get to about 55 meters, they reach their top speed. They reach their top speed. So that's 55 meters. That's their top speed. And now they're maintaining that. And this is really interesting. By the time they get towards the end, can you tell me what's happening to the graph here? You know the gradient represents the speed. They're getting slower, aren't they? They're getting slower. So Usain Bolt, when he broke the world record, actually broke it in 2009, he did 9.58 seconds. 9.58! That's mad. 9.58 seconds. But he got slower. Can you see? He's steady out of the blocks. And then now it's going fast. 35 to 55 meters, really fast. When he gets to about 70 meters, he's now tiring. He's slowing. And this is amazing, boys and girls. By looking at the graph, When you see Usain Bolt in a running race, it looks like he's getting fast, he's beating everyone else. The gap starts growing. But he's not. He's actually getting slower. Can you see the gradient? It's really steep, and it gets a bit less steep. Can you see that? It gets a bit less steep. He's getting slower. But here's the key point. The other runners get even slower. So it looks like he's pulling away from them. But because he's getting slow, but they're getting even slower. And that's amazing for me, because it shows that mathematics can help us understand what we see with our eyes. With our eyes, we look as if he's getting faster, but he's not. He's getting slower. But the other people, they're getting even slower. And that is the power of mathematics with speed, distance, time graphs. There we go. So that is the end of the session. And we're going to look at thoughts of Miss Seagull and how it's related to this. So, there we go. So we've got this, remember? Time and then the distance. So this thought actually is related to the concept of time. It's really important. And I've got a couple of questions coming in from parents as well. A couple of shout outs. So Amani Khan's been waiting all week for the session. I'm really pleased. So thank you, Amani. How fast can I run? If I be honest, I've done once, and your parents might be impressed, the adults and carers. I once on a half marathon in 1 hour 28, and that's not too shabby. Half marathon is 21 kilometers in 1 hour 28, which is 60 plus 88 minutes. And that's not too bad, is it? Okay. So the thoughts of Mrs. C today. So again, if you've got any ideas, actually, one thing I'd like you to do, homework is, we did the speed, distance, that graph with the axis on time there and distance there. Can you show me a poster, send it on Twitter or Instagram or TikTok at Bobby_Seagull and at Explore Tutors, and I want you to show me your journey to school. Obviously, we're at home now in isolation. Your journey to school. Can you show that to me and send a picture of it? Your journey, obviously, you start, let's say, 8:30, you go to school, let's say 5 kilometers, you'll be in school all day, you might go to the park for PE. So do that and send me your pictures. Send it at Bobby_Seagull, at Explore Tutors, send it on Twitter, Instagram, Facebook. We love to see your ideas, or TikTok as well. Okay, so here is today's thoughts of Mr. Seagull. Don't forget your homework, and I will shout out a few little homework for Key Stage 2, and I'll shout them out next week on Wednesday. So, there's a professor in America called Cal Newport, and he's a professor at Georgetown University. And he was thinking, why do some students spend all their time with their books, they're revising, and they struggle? And other people, they don't seem to spend much time, and they seem to be quite confident in the lesson. It's nothing to do with intelligence, actually, nothing at all to do with intelligence. It's to do with intensity. And look, write down this formula. So it's work accomplished, if I can write that, accomplished, you can, work accomplished equals time spent, because we've been doing time this week, multiplied by intensity. Work accomplished is, and this is the secret to success, according to Professor Cal Newport. I'll tell you how this works. Imagine you've got two students, both preparing for a big exam. Oh, people are asking, what's the topic next week? The topic is, let me double check. I should know, as I prepared this yesterday. We're on to measurements next week. So measurements, so length, weight, capacity, estimation of that. So measurements is next week. Thank you. Okay, so work accomplished equals time spent times intensity. Imagine two people want to get 30 units of output, 30 units. And again, that's like an arbitrary measure, but 30 units of output. One person spends 10 hours, and they work at an intensity of 3. And 3 is a mark out of 10 because they got music on, all they're doing is highlighting their notes, they're chatting to their friends on their phone and WhatsApp, checking Mr. Seagull's Instagram stories. The intensity isn't very high, but they get 30 units done. Someone else is focused. razor sharp focus. They've got their music on low, they've closed their door, they're all ready, their phone's not on, and they're not just highlighting the notes, they're actually doing practice questions. Their intensity is 10. They're focused. How long do they need to spend to get 30 units of output? Only 3 hours. And they still get 30. Only 3 hours. If you look at these two students, they both get the same amount of work done. One's not smarter than the other, but it's because this person has a greater intensity. Remember, work accomplished is time spent multiplied by intensity. This one here is sort of fixed. You either put 3 hours, 5 hours, 7 hours. But this intensity is in your control. When you're working, can you please make sure that you are focused? You've got again, most people, got your music off, your phone away, maybe your television on. So, this is the key thing. Work accomplished is time spent multiplied by intensity. If you apply that intensity, you will get more done. So, the last few things, let's see, what have we got? A few shout outs before the closing messages. Sasha's done all his work. I'm really pleased for you, Sasha. Who else do we have? Elliot and Haringa, age 9, 3 squares. James Harrison wanted a shout out, and you can't wait. Amisha came to all the sessions. James says I'm very clever. Thank you, but all of us can be clever if we put our minds to it. Beatrice asked about how I'm doing really well. Thank you. Mayur is in year 4. Thank you for coming. And you're going to miss these classes after. I'm going to miss these classes too, but we're going to keep going. We're going to keep going for now. And James Harrison got a shout out. So, on a couple of quick announcements. One is I do a quiz for NHS I'm going to answer a couple of questions. A quiz for NHS every Saturday at 8 p.m. on my YouTube channel. So you go to Bobby Seagull YouTube, 8 p.m. It's fun, charades, music, me singing very badly, and some maths questions. Okay, so a couple of questions were, one is, how can I improve my multiplication skills? So next week, a couple of people asked, we're doing measurement, length, weight, what else are we doing, Irene? Length, weight, capacity. So, Eloa says, how can I improve my multiplication skills? And I think, Eloa, for multiplication, it is one of those things where you have to practice out. So imagine you're doing 7 times 6. Some people use apps to play the games. Other people repeat it. 7 times 6 is 42. And I think for multiplication, you do need to get it memorized. Eloa, thank you for that question. There's another question from a parent that says, are there any good podcasts? I know young people prefer YouTube, but podcasts are sometimes a good way of focusing and listening. But actually, you find if you're watching things sometimes, like a video, you might be looking at the video and enjoying the atmosphere there. But if you listen to a podcast, you're more focused on the audio. So, for Key Stage 3, a couple of recommendations. One is something called Oxford Sparks Big Question. And we've shared this on Twitter as well, by Oxford University, and it's really good for STEM, science, tech, engineering, and maths. And you can look at questions like, can computers predict crime? Or, how do we turn a plastic bag into fuel? That's Oxford Sparks Big Question by Oxford University. And then the final one is, Mr. Seagull's got a podcast. It's called Maths Appeal. Again, if you look at my Twitter, my Instagram, it will be there. It's called Maths and then Appeal. And this one is, we interview a famous mathematician every week, and we talk to them about their mathematical journey. Maths Appeal. And we cover different topics. It's really fun. We do puzzles and problems. Maths Appeal. That's on Spotify, iTunes. So let's have a look. Any other questions coming up? I think we're probably done for questions. So next week is measurements. Again, Monday's Key Stage 1 at 10. Wednesdays, what do we have? Key Stage 2. And then Fridays, Key Stage 3. And again, Explore Learning. We're here at Explore at Home to help you this difficult period. And then go to Explore Learning UK, free resource. So you can watch all my videos again, all of them again, and you can download an activity sheet on the task today. And again, they're offering currently a free online trial, and you can find more information on the website. And again, we love social media at Explore Learning _official on Instagram, at Explore Tutors on Twitter, and I'm at Bobby _Seagull on Twitter, Instagram, TikTok, Facebook, everywhere. You guys have been wonderful. And again, we're going to end with our maths dance. I'm going to a shout out because you've been brilliant today. You've been so patient. So Beatrice, Bournemouth, age 10. Bo, thank you for taking part today. Tom, thank you. Lena, thank you so much. Pfizer, Edwin's been great today. Lena says she's the best. Yeah, you're one of the best. Lots of people here. Sean, James Harrison, Beatrice, and again, Sathina's, I think, son. And don't forget the homework. Send me a picture of your distance time graph for your journey to work. And that's the homework. Remember, before we do the final, I can do maths wrap. Don't forget, remember the little wrap for the graph is time is independent. Time is on the x-axis. Distance is dependent. Distance on the y-axis. Time is independent. Time is on the x-axis. Distance is dependent. Distance on the y-axis. Time is independent. Time is on the x-axis. Distance is dependent. Distance on the y-axis. There we go. So thank you. Thank you so much, Zach, KCH2, Bhavna, T, and you know how we all end every session? We have a positive maths wrap. Yug, age 10. Sean is going to do the homework. Thank you, Cledwin. Thank you for James and Chesterfield. We're going to end with Zach. Thank you, Zach. A big shout out to Zach because Zach did the homework on Babylon. Thank you, Zach. That was brilliant. Bye from Erin and Northampton. So here we go. The maths wrap. Remember, we're going to do this 3 times. 1, 2, 3, go. Yes, I can do maths. Yes, I can do maths. Yes, I can do maths. 1, 2, 3, 4. Yes, I can do maths. Yes, I can do maths. Yes, I can do maths. And there's the finale. It's going to be really exciting, Sean and Serene. 1, 2, 3, go. Yes, I can do maths. Yes, I can do maths. Yes, I can do maths. Thank you all so much, and thank you for being so patient. See you next week. We're Explore Learning, and we're keeping the learning and education going. Thank you all.